Okay, we have programming assignment 2 that's due November, and there's also a midterm, and it's in this building, room number 2, wherever room number 2 is. And today's plan is to talk about hashing and to talk about universal hash functions and collision resolution policies. But before we talk about that, we have to play a game. So here's the game. This is called Petals Around the Rose. So that's the name of the game, Petals Around the Rose. And the game involves dice, which I brought, and we roll the dice and produce something like that, and then we say, oh, that hashes to a number between 0 and 20, and we put in whatever that is into that. So this is 2, 2, so it hashes to 0, and 2, 2, 4, 6, 6 is what hash to 0. Okay? So that's the game. We're hashing. It's kind of a weird game because we're generating a number, or we're generating something to hash, like this thing. We're generating at random. Sorry, can you see that? Okay. So this one is here. This is a 1, 5, 5, 5, 6. And what's the game? The game is you're supposed to figure out the hash function. So I'm calculating a hash function. It's a deterministic hash function. You give me numbers on a dice, 5 numbers on a dice, and I can tell you the place that it goes to in the hash table. And you have 2 clues. One is the name is called Petals Around the Rose. And the second clue is that this is the list of all possible, well, you know that you can't have more than a number 20. So, for example, if you were thinking it was the sum of the numbers, that's not right. Okay? Is the game clear? We have to figure out what the hash function is. Anybody know what the hash function is right now? Yeah? You know already? Okay. Well, let's do some more. You need more data. Oh, that's a 4. 1, 1, 2, 2. 1, 1, 2, 2, 5. That's a 4. It hashes to 4. It's some function of those outcomes of the dice. Let's try it again. It's a fun game. I don't know if it's a game. It's a puzzle. This one is a 8. So it's 2, 4, 5, 5, 6. When you figure it out, raise your hand. Or if you think you figured it out, raise your hand. Looks like a 6. Two, 3, 4, 4, 5. Also, for those of you that have figured this out or know it already, you can check my work. And if you do have a guess, You can guess, and then I'll tell you whether you're right or not. What do you think that one is? Six. Another six. So this is another six. 1, 3, 3, 3, 6. Petals around the rose. It's a clue. And that the numbers only go up to 20. So in fact, I will tell you, the thing that has the most, the one that goes in here is 5, 5, 5, 5, 5. And it's the only one that goes there. It's like playing Yahtzee. This is 3 of a kind in Yahtzee. 3 twos. But in this hashing scheme, it's 6, which is getting well populated. So this is 2, 2, 2, 3, 5. It also goes into 6. You want more clues? Or should I just keep rolling dice? So eventually we go. What's 19? It depends on the dice that form 19. So it depends on which symbols I get on the dice. Like if, for example, this one is, let's see, how could I get, that's a good question. This one would be 10. That would be 8. That would be 6. That would be 6 as well. That would be also 6. That would be 10. Petals around the rose. Has something to do with the picture. If I just rolled one dice, I could hash one dice for you. Should I do that? That's a 4. That's a 0. That's a 0. That's a 0. It's a 2. It's a 4. It's a 0. 0. Petals around the rose. 4. 2. How many people think they have it? Okay, good. Because I'm getting tired of rolling dice. So the trick is that you treat the dice like a picture, and the rose is the center spot, and the petals are the things that are around the center spot. So this is a rose with 2 petals. This is a rose, that's a rose with 4 petals. That's a rose with no petals. And these aren't even roses. Whatever the other one is. 2. There it is. Okay, petals are on it. Yeah. So it only hashes the even numbers. Yeah. It's not a very good hash function because all I'm getting is, I'm only getting things like, 2 or 4. The other thing that's a little bit weird about this is that in this case the hash function is fixed. And the things that I was hashing, the items hashed, which were rolls of the dice, were random. And what I want to convince you of is that that's not the way the real world works. In the real world, items to be hashed are chosen, not to make you paranoid or anything, evilly. Is evilly a word? They're chose with malicious intent. And to guard against that, we want to choose hash functions at random. So this is a reality. Well, we've been playing as a game, it's sort of the flips of that. But in any case, it's a fun game. And now you can play this game with people, and it takes them a long time to figure it out. It'll be fun. Especially if it's a drinking game. But I wouldn't know anything about that. Okay. So last time were talking about expected value, and we had just talked about the definition of expected value. If I have a random variable, for example, this index that we selected when I rolled the dice, that index is a number that depends on a random thing. It depends on the rolling of dice. And so I could treat this number as a random variable, and I could ask questions about it. For example, I could ask, what's the expected value of that random number? One thing we know about that random number is that it's always even in that case. But what would be the expected value of that number? Well, sort of the expected value is like the average number, or what you would expect to get. If you kept rolling this millions and millions of times, your table would fill up and fill up and fill up. And if you kept putting a mark down for every spot in the table that was hit, you would get some sort of distribution on those spots, and you would want to understand what's the average of the numbers that were produced according to that distribution, according to that probability. That's what expectation is. The expected value of a random variable is exactly that. It's saying, take the probability that the variable gets a particular value and multiply it by the value, and that's averaging up all the values according to that distribution. So if the distribution was equally likely, like, for example, when I roll one dice, then the probability for each of the outcomes is 1/6, and I get something like, for one dice, is it one die? It seems kind of grim, doesn't it? Anyway, I think that's what it's called. You get 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3. You get the picture. Dot, 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 which evaluates to what? What's the random outcome of the dice? Expected value. 3.5, 3.5. Okay, so now the other question is, if I roll two dice, then I have now 36 possibilities. When I roll two dice, there's one of them. The first dice came out 1, and the second one came out 6. The first one came out 6, and the second one came out 5. Each of those possibilities is shown in this table, and the sum is shown in the table. And what's the expected value of the outcome of 2? Well, you just say, well, there's probability 1 out of 36 that I get a 2. And there's probability 2 out of 36 that I get a 3, etc. And what is the expected value of the roll of 2 dice? The last thing is 1 out of 36 gives you 12. What's the expected value from this? Not 7 over 36, but just 7. So if you learn anything from today's lecture, it's the next thing, which is that if you have two random variables and you're trying to understand the expectation of their sum, that expectation is the sum of the expectations of the individual variables. So the fact that we knew that one dice has expectation 3.5 means that we just can add 3.5 and 3.5 together to get the expectation of the sum of those two random variables. This is true for all random variables. It doesn't matter that they're independent. If you're thinking it matters, it doesn't. Like if I roll this dice, it has probability, let's say this dice has a probability of coming up a particular number with probability 1 out of 6, but this dice, I cleverly have calibrated it so that it always lands the same. What is the expected value of the sum of these two weird dice? I roll one, and oh, look at that. Amazing. They're always the same. Oh, no, that was unfair. One. Wow. What's the expectation of the sum of these two connected dice? Assuming that the random roll for 1 is giving you an expectation of 3.5, you know what the answer is. This condition doesn't require that these random variables be independent in any way. We know that for these two, the expectation should be 7. Again, the sum of these two random variables should be 7, even if they're not independent. Okay, so if you get anything out of the lecture today, that's the thing that's probably most useful for your life. I know you don't think it is, but it will be. Okay. So when we look at birthdays, which is what we were looking at before, and I wanted to do this calculation, but it turned out to be really, really messy, and it looked like 365 divided over 365 times 364. Oh, wait, hold on. Need this anymore? And it had this really long mathematical expression. Now let's do it with expectation. So if I have a bunch of people like you in this room, what's the expected number of people that share a birthday? Different people that share a birthday. Like you share a birthday with yourself, but different people. So we could say, let a random variable xij be 1 if person I and person j have the same birthday. Okay? And 0 otherwise. What is the probability that person I and person j have the same birthday? If their birthday is chosen uniformly from 1 to 365, what's the probability that these two people have the same birthday? I'm like, if you were random people? You're not random, you're mystics. Anyway, I pick 2 of you. What's the probability you have the same birthday? Now, I have to tell you that if you're a newspaper editor, your answer might be 1 out of 365 squared. That's what the newspaper editors say about the fact that some lottery number was chosen in the state of Illinois, and it was the same winning number as was chosen in California, and they said there's 1 billion possibilities for the number in Illinois, and 1 billion possibilities for the number in California. So the probability that that happened was like 1 over a number that's a billion times a billion. Another fact you can take from this class is that is not true. Because once they've chosen the number in California, what's the probability that they match the number in Illinois? 1 in a billion. Right? There's a number that you're shooting for. If you happen to get that number, which is a chance of 1 out of a billion, so now tell me, what's the probability that 2 people in this room share a birthday? 1 out of 365. Okay? So the probability that, I'm going to write it this way, the probability that xij equals 1 is exactly 1 out of 365 because we are disenfranchising the leap dayers. And so what is the expected... So if we wanted to find out the number of pairs that share a birthday, that's this value x, we would sum up over all possible ways of pairing people up, which is choose person I, who is less than person J, because we don't want to have, we don't want to have counting people pairs twice. So I've got to count you just once. So I'm saying, look at person I, look at person J. If they have the same birthday, then that contributes 1 to my sum of the pairs that are same birthday. And this is another random variable. So x is another random variable. It's a sum of a bunch of little random variables. These are called indicator random variables if you are taking score. And when I sum all of these up, I get the answer that I want. Now I want to know what the expectation of x is. What's the expected number of people that have the same birthday in this class? Now I use linearity of expectation, which is the fact that expectations sum nicely. And so I get that the expectation of x is equal to the expectation of the sum, which is, I can take the sum outside. So now it's the sum of the expectations. So now you have to tell me, what's the expectation of ij? What's the expected value of the random variable that says these two people have the same birthday, and I'm 1 and 0 otherwise? What's its expected value? Everybody okay? Maybe this is going too slowly. But it's, by the definition, the probability that x takes on a particular value, and x only takes on 2 values, 0 or 1. So it's a probability x takes on 0 times, well, who cares? Because if it's 0, then this product is 0. So it's the probability that x equals 1 times 1. And the probability that x equals 1 is 1 out of 365. So this summation overall, I less than j, you guys know what that summation is. I'm saying that the numbers are, let's say there are k people. How many pairs are there of distinct people in a room with k people? Please. Somebody. K choose 2. K times k minus 1 over 2. But this is the number of numbers from 1 to k, such that I can pair them up. 1 is less than the other. It's like a for loop that's going for I equals 1 to k, and then for j equals I plus 1 to k. How many times does that execute? It's the same thing. This is k times k minus 1 over 2 times 1 over 365. Okay, now why are we going through this exercise in probability for today? Besides the fact that it's really important for your life to understand probabilities so that you can make rational choices in certain situations. Besides that, it's also important for hashing because if we are hashing k things, maybe people, into m bins, our hash table, and we happen to use a random hash function, something that hashes people uniformly across all of the spots in the table, an ideal random function, which is an assumption that's not true, but let's suppose that we had this ideal random function that hashed everything uniformly. This says that we would expect that if we hashed about this many square root of m plus 1, that we would see a collision. That means that for a table of size m, it's really only useful if you don't allow collisions for square root of m things. And square root of m is really kind of tiny compared to m. We don't want, think of it this way. If you're hashing n things, you don't want to use a table of size n squared. It's too big. But that's what we're facing. we're facing this sort of. So when we look at these hash functions, we are going to have to deal with collisions. Is it okay? Does it make sense? It's like a very long-winded way of motivating the fact that we have to deal with collisions, but it introduced all this probability stuff, which is cool. Okay, so you remember our hash function. Our hash function is mapping into a table of size m. And just as a warm-up, we will look at example of hash functions for hashing strings into a table of size m. This is the suggestion from last time that when I hash a string, what I should do is treat it as a number. So in C++, a string is a sequence of characters. Each character is 8 bits. So each character is 8 bits. That means there's 256 of them. It includes all of the letters in the alphabet, capitalized letters in the alphabet, a bunch of weird symbols, and some very strange things that were put in there for weird reasons, historical reasons. This is the ASCII coding system, not Unicode. If you want Unicode, that's where you can get like all the character set for all the languages in the world as long as they've applied to the Unicode Standards Committee. Then that's called a W string, a wide string. This is just a string. So each character is 8 bits. And what this does, what this loop does, is it calculates the bit representation as if that was a number for the entire string. It concatenates the 8 bits together like this. That's a gigantic number, and it takes it mod m. But it does it in a clever way. It does it using Horner's rule, which is basically to say that if I wanted to multiply something like, if I wanted to get, let's say I had something like x1 plus x2, no, so Horner's rule is using hold on just a second. I start with x. Let's call the first character of the string x1. I would like to calculate x1 times 256 to the 0th power. I want to add to that the second character, x2, times 256, so I shift it over by 8 bits so I don't overwrite the character x1. I want to calculate 256 squared times x3, add it to that. I want to calculate 256 cubed times x4, etc. So for each character, starting with the smallest, the first character, x1, I want to increase the amount that I'm adding by a factor of 256. So one way to do this is to start off with the last character, let's call it x sub whatever it is, n. And then that's right here. I is equal to the last character. And I treat the my current value of the hash function is 0, and I add xn to it, and it's 0 times 256, so that's nothing, and I get xn. Now when I do the next loop, I multiply xn times 256, and I add xn minus 1, and then the next loop I get 256 squared xn plus 256 times xn minus 1, and I add xn minus 2, and you see I'm going to eventually get that. So this is trying to get powers of 256 times each of the individual characters in the string so that it's treating the string as a big, huge number. And then it's taking it, as we go along, mod m. Okay? And it does it by a constant number of operations per character. One multiplication and one mod per character. Does it make sense? Maybe not. Yeah.
Well, how come we're able to get into progressively higher powers of 256?
Oh, because I'm doing whatever the previous hash function was, I'm multiplying it by 256. So if I look, this is the current hash function, this is h, and suppose I had another character, then what I get is 256 times h plus the next character, which is, in this case, xn minus 3. And that's equal to 256 cubed xn plus 256 squared xn minus 1 plus 256 times xn minus 2 plus xn minus 3. So each time that multiplication is multiplying the entire sum. Yep.
So you take the mod of it every time, right?
I take the mod of it every time.
Why does it accumulate?
Because I'm taking it mod, it's going to accumulate, and it's, I'm modding it each time, so I'm sort of killing it back down to the range that I'm interested in. So I'm taking the remainder division by 4.
H is always less than n, right?
Right. So think about postponing the mod until the very end, and you would get this. Right, if I didn't do the mod every single time, if I just added it all up, and then I took the mod m, that would make sense more to you?
Yeah.
Okay.
But it's the same thing. You take mod every time.
Yeah. So, okay. So now, yeah. Because I want to actually get an index that's going to, well, two things. I want it to be an index into my table. My table is of size m. And the second reason is because I have a computer that can't handle arbitrarily large numbers. It can't do arithmetic on arbitrarily large numbers. So I have to choose something that's small, and I'm going to knock it down by mod m. Of course we'll get two strings to the same hash. I mean, this is going to be the point of this whole exercise, is that, I mean, this seems like a good idea, and in fact, it is a good idea. You take a string, you treat it as a big number, take it mod m, it's a great idea. But it means you're trusting that the people that are using your hash function are going to provide you with nice strings. They're not going to provide you with strings that all hash to the same location, that all turn out to be the same mod m. Also, it really only depends on a few number of characters, usually, unless m is chosen to be prime, something like that. Okay, I wanted to show you something from real code. So this is the hash table that's used inside of Yak. How many people know what Yak is? Wow. This is the first class. So look, you don't know about Yak because nobody needs to know about Yak at this point. But it's the first class that nobody knew what Yak is. Yak stands for Yet Another Compiler. Yet Another Compiler. So it's a compiler, and it's yet another one, as if they needed more. So it was written when there was a push to write new programming languages all the time. And what a compiler, or at least what Yak does, is Yak takes in a programming language description in source code, and it parses it. It tokenizes it. It understands what characters, sequences of characters are important, like in C++, the character sequence int is kind of important. It's declaring an int. So it understands that, and it parses it into a thing where it can pass on to the compiler that can say, oh, okay, I know what to do with ints. I'll do the following thing. So it's the mechanism by which you can translate a language into something that the computer can understand. So it's like a compiler pre-compiler. That's why it's called a compiler-compiler. Anyway, Yak has in it, as you might expect, it has a hash table because when you write a program in C++ or C or whatever, you use variable names. And those variable names are going to be declared as something, like maybe an int. And then the compiler is supposed to be checking to make sure that that variable name, which was declared as an int, is actually, when it was used, it's used as an int, and it's not used like as a string, or it's not used in some other place that is not supposed to be used where it hasn't been declared. And so it has to look up names, like the variable names that you create, it has to look them up in a hash table. This is the hash function that it uses. I have to tell you that Yak was written in about 1970. So back then, it was very important that things be fast. So what do you see in this code that's different from the Horner's method, Horner's rule multiplication code? I see one thing. The number 31 versus the number 256. That's one difference. But what's another difference? By the way, 1970, that was back before there was C++. So there were no such things as strings. They were called character arrays. And that's why this is a character array. Yeah. Yeah, this crazy thing. What's this doing? Well, this is a binary AND operation. Table size is a power of 2. What would table size minus 1 be? Table size is a power of 2. Table size minus 1 is, it's a sequence of ones. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. So this is called masking. So instead of doing a mod operation here, we're doing a cheap mod. A cheap mod says mask out all the bits except for table size minus 1 value number of ones. So it's using a mask, oops, mask rather than mod. Why? Why are they using mask rather than mod? Yeah.
I think like when you mask something, that's like greater, less, or equal to like your decimal 2, like it's equivalent to mod.
Yeah, it's equivalent to mod, but why would you use it instead of mod? Yeah. Yeah, it's faster. This is a lot faster in old computers. So what we're getting here is essentially exactly the same code. This loop, I mean, look, it's really optimized because it knows that the string is null terminated, which means the last character of every string in C is a 0, is a null. So it says while star s, and that's all it needs to do to loop through the string. It increments s here, and it's all very, very clever code. It's very tight code. No one would write this code nowadays because it's nearly inscrutable. You can't understand what's going on unless you look at it for a long time. But it's fast. And so it's great. It's implementing a hash of a string into a hash table. And it's doing it essentially using Horner's rule, except that it's not really making things not overlap. It's using the number 31 rather than 256. And it does that because that kind of mixes things up a little better than using 256. The multiplication, the fact that it's smaller than 256, means there's some pollution between the bits of the part that you've already hashed and the part that you're hashing next. So it sort of, they thought, worked better. Everybody happy? Just reasonably happy? Yeah.
What's the purpose of H?
Oh, what does this mean?
Yeah.
That means star S means dereference the pointer. So S is a pointer to characters. S is the pointer to the character that's actually at the start of a string. So star S is the first character of the string. And then star S plus plus, what the plus plus does is it post increments. So that pointer S is a pointer to an integer. S plus plus is another pointer. It increments S by 1 to point to the next character in the array. This is the evil, bad thing that C allows you to do. It allows you to do arithmetic on pointers. So you can add what you want to a pointer, and you will get another pointer. And if that allocation, the memory allocation, happened to be a sequence of integers consecutively in memory, you would get the next integer in that sequence. So it's a fast way to get.
The same as like initializing H.
No, it's initializing H to be the first character.
Why not?
Because that's the way Yak did it. I mean, you could do it that way.
Right? Just like.
But why would you not do it? You would save one assignment operator, which is what they did. They saved an H equals 0 assignment operator. That assignment is not necessary. You can just initialize it to be the first character and you don't have to do anything. So for one character variable names, it's fast. It doesn't even enter the loop. Well, it does, just to say, oh, star S is 0. It's cool. Okay, why did I show you this? Because I wanted to emphasize the fact that fixed hash functions are dangerous. So this is a fixed hash function. Yak's hash function is a fixed hash function. And we talked about this last time. If there's somebody out there that can cause many elements to hash to the same slot, then they can execute a denial of service attack on your web server by requesting keys that are all hashing to the same location to be stored. And that set of keys would cause the performance of the hash table to be much, much worse than it would be if the keys were evenly distributed. So why would she do this? Is for denial of service. She's evil. Or maybe not. Could be she's fighting climate change and she's targeting some oil company's website. Maybe that's good. I don't know. It's a dilemma. Usually it's not good to do that kind of stuff. So anyway, Yak, which has this type of, this is the sort of expanded version of its hash function, or the mathematical version of its hash function. Yak has this interesting property that if I hashed capital XY and lowercase xy, I get the same hash value. So if you use the variable capital XY and the variable lowercase xy, those two would hash to the same location in the hash table. So what? So this is the part where I'm training you to be malicious hackers. So if you knew this fact, which you now know, how would you generate, knowing what Yak's hash function is, how would you generate many, many keys that are different but all hash to the same location? I'm going to wait a little bit, just so that people can think about this. Unless you have a question. You have a question? Okay, everybody good? How would you do it? You know how to do it?
Would we just do a string where we have like the same letter, but like in all, we'll have a string composed of just the same letter, but it'll be written in such a way that it's alternating between the capitalized and lowercase version.
Oh, you think that WW hashes to these two hash to the same thing?
Or like capital, what's that? Pair and alternating pair.
Oh, sorry. You want capital AB and lowercase ab is the same as lowercase ab and capital AB. Is that what you're saying? Okay. It's actually true. It's not true for AB. It's true for XY. But X and Y are particular characters. So I'm going to say, this is your suggestion. Your suggestion is create this string. XY, XY versus XY, XY. Think this will work? Will these hash to the same location? You know the hash function. It's right there. What happens in these two strings is that there's some hash value for xy, and that's part of the hash function for lowercase xy, capital Xy. And then there's another part of this hash function that's the lowest part of the, but these two things are the same. We know that if you just gave me x times 31 plus y mod 1023, lowercase x, lowercase y, then that would be the same as capital X times 31 plus capital Y mod 1023. So this is saying whatever capital X times, I guess I'm writing it as 31 times capital X plus 1 times capital Y equals 31 times lowercase x plus lowercase y. And if I multiply that by, so this is true, this is what this condition says. This is true, then when I multiply this by 31 squared, I get 31 cubed x plus 31 squared y equals 31 cubed lowercase x plus 31 squared lowercase y. And so no matter how I add these together, I get the same thing. If I add these two, it's the same as adding these two. So if I have lowercase xy followed by capital XY, it's the same as capital XY followed by lowercase xy. In fact, capital XY followed by capital XY is the same as lowercase xy followed by lowercase xy. So now what do? Well, you just generate these strings where you have capital XY or lowercase xy repeated as many times as you want. Pick one or the other, repeat k times, you'll get a string, and it will always hash to the same string as everybody else. So that's essentially what happened. That's what happened with Java in 2011, and Python, and Ruby, and PHP. All these things suffered from an attack that was like this, because they were using a multiplicative type hash function like the one that we just saw, the yak function. And so what do you do to protect yourself against that? In a minute. Well, one thing you can do is you can use a cryptographically secure hash function. What a cryptographically secure hash function is that even if I give you the outcome of a hash function, of one of these cryptographically secured ones, even if I gave you the outcome of that, you could not find another item that hashed to that same value. It would be computationally infeasible for you to do that. It would take you too long. There's too much to do. So these things supposedly exist. They're called secure hash 512, or secure hash 256 was the old one, or secure hash 1024 is the new one. They keep getting bigger because computers get faster. That's one thing you can do. Now, the second thing you can do, the problem with these is they're very slow. Second thing you can do is you can choose a random hash function from a small set. And that's what we'll talk about next time.